Let's consider a satellite in circular orbit around a central point. There are some equations that will describe its motion, and there are a few things that I want to discuss about this motion and that satellite and its central point that it's orbiting. First, I want to look at the potential energy of that satellite relative to both the central point that it's orbiting and very far away. And then I want to look at the equation for its motion around that central point, and then what it would take to get that satellite to no longer be a satellite of that central point and instead move very far away. So let's start with the application of fundamental principles, forces, and energies to derive an equation that describes the energy of that satellite relative to the central point. Now, here's the thing about this. We already have an equation for the potential energy of that satellite. We call it mgh. Here's the problem. We're assuming with this equation that g is constant. But it's not. Since g is not constant, we can't use this equation anymore. We can only use this equation for the special case where the height that's being described is very small relative to the radius of the planet. And when the height is very small relative to the radius of the planet, then g is constant. So we can't use that. What we're going to end up using is the combinations of Newton's law of universal gravitation and the relationship between force and potential energy that we discussed before when we looked at potential energy versus position graphs. So when you have a potential energy versus position graph, the force of that terrain on an object, let's say a mountain surface on a bowling ball, depends on how steep and in what direction we're looking. Now, here's the derivative form, the differential relationship between position and potential energy, which will get us the force. Take the derivative, get the slope of that line, throw a negative at it, that gets you the force. But we can go in the other direction as well. Negative stays, multiply both sides by dx, and then undo the derivative, find the antiderivative. So we have the integral form and we have the differential form of the relationship between force and potential energy. And we're going to take Newton's law of universal gravitation and put that into this integral. Now, this x, we only did one-dimensional things before. Now we have a three-dimensional system, and instead of doing only along the x-axis, now we're going to do a radial structure. So all of the x's are going to turn into r's. All that simply indicates is that we have a radial structure and not a linear structure. And, oh yes, we have a minus sign here, and we have a minus sign there. So the minuses go poof. Now, what we need to do is we need to say, actually, let's back up a moment and look back at this potential energy equation. We took a particular place as having zero potential energy, and we call that the floor. So we said, hey, if you're on the floor, you have no potential energy because you can't fall. If you're on the second floor, you have no potential energy until I dangle you out the window. If I dangle you out the window, all of a sudden, you could fall. You're a height above the floor because I moved the floor on you. But what that indicates is that potential energy is arbitrary. there is no absolute zero for potential energy. Since there is no absolute zero for potential energy, we have to figure out a place where the potential energy is zero. And when we look at this equation, the place where potential energy is zero is the place where this fraction goes to zero. And this fraction goes to zero, it approaches zero, when R approaches really far away. So that would be the case of we have the satellite, but we could be very far away. And what we're going to do is we're going to start with the satellite very far away, and we're going to bring it in towards our planet. So we're going to start with it's very far away, and that means that there is effectively no potential energy. So I should have an arrow here. And then we're going to bring it in to a definite position. R is equal to R. So that would be a radial distance away from the center of the planet. And now it will have some potential energy relative to the planet. On the left side, our integral, our antiderivative, will go from a du to a u, and the du has done its job. On the right side, constant, 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 that goes along for the ride. 1 over r squared, the antiderivative of 1 over r squared is minus 1 over r. And we're going to evaluate that between very far away and right here. And our constants go along for the ride where we have our central point that is being orbited, that's the planet. And then we have our satellite. If you want to do the subscript thing, we can do planet and satellite. That doesn't really matter. Just indicate we've got two masses here. And lo and behold, our minus sign has reappeared. This is an indication that as you move closer to a planet, you are moving down into a well. That's why we call this gravitational wells, because you're falling down. If I put a proton 1,000,000 miles away from the Earth, and there's nothing else in the universe, and I just let it go, it will fall towards the Earth. It will fall down into the potential well created by the existence of the Earth. Evaluating at our limits, we're going to have u minus 0, and then here we're going to have minus gmm over r minus a negative gmm over really big. Now, a standard AP problem is what is the change of potential energy between these 2 points? So instead of saying we're going to start very far away and then we're going to come into here, they might also ask, I'm going to start out with an orbit at radius a, that's yay big, and then I'm going to move to a different orbit of radius b, that's yay big. At which point, instead of having a 0 and a u, we've got UA and UB. And then here we're going to start at A and we're going to go to B. And you're going to notice that instead of having, well, this guy is 0 here because we have an infinity in the denominator, we're going to have potential energy at A versus potential energy at B. This is sort of like, I'm going to start on the first floor and then climb the stairs and go to the second floor. What's my change in potential energy relative to the ground outside? Well, at that point, it doesn't matter that you started on the first floor and went to the second floor. We don't care about the ground outside. All we care about is the difference between the 2 floors. And that's what we're doing here, even with the infinity and some position. But what this has given us is the fact that potential energy around a planet, or a star, or a galaxy for that matter, follows this form. Universal gravitational constant, the mass of the thing that I'm going to be going around, the mass of the thing that, well, is me, and then how far away from the center of that thing am I? And by the way, I'm falling down into a well. This, by the way, from here all the way down to here, actually including this, before I substituted in, shows up reasonably frequently as part A on AP test questions. So you need to not just know the end result is, hey, I can use that equation, I can plug in numbers and figure out what the potential energy is. You also have to be able to get it. So you have to be able to go from Newton's law of universal gravitation all the way down to, and including, here's my expression of the potential energy as a function of radial distance from the center of the planet. Now, let's use this to analyze two situations. We're going to start with circular orbits, and then in a little while, we will look at non-circular orbits when we look at Kepler's laws. But for right now, let's pretend that you have a satellite in circular orbit around a planet. So here's our rocket at a radial distance from the center of a planet. Remember that when we're talking about gravity, you have to measure everything from the center of the planet. And if we're talking about circular motion, we have some forces acting on that satellite. And for our purposes, we're only going to have two objects in our universe, the planet and the satellite. I don't want to deal with something else muddying the waters. And when that's the case, we don't have an actual string tying this. What we have is the force of gravity, force of gravitational attraction between the planet and the satellite. So on the left side here, we're going to have the force of gravitational attraction between them. And then the satellite, so let's use our subscripts here, satellite, u squared over r, for circular motion. Now, let's just do one minor adjustment. Let's get rid of one of those r's. So you cancel, you cancel. This guy on the left should look very familiar because we just got almost that. We almost got that. We're only missing a minus sign. So as soon as we canceled out one of those r's, what we end up with is, hey, that's potential energy. If this is potential energy, this also has to be some kind of energy, and the mv squared should tip you off that it's kinetic energy. And since I said satellite, this thing is going to be moving. If it's not moving, it's not a satellite. It's just falling into the planet. It's going to crash. So since that's moving, that's kinetic energy. But we're missing a 1/2 here because kinetic energy is 1/2 mv squared. So if we multiply both sides by a 1/2, so we've got 1/2 and we've got 1/2. This side is kinetic energy, and this side is 1/2 of the negative of potential energy. And what we have here is we started with forces of an object in orbit, and we ended up with the energies. Now this only works, this is a special case relationship. And the special case is it has to be for circular orbits. Now when you have a satellite in a circular orbit, what you get is the kinetic energy is going to be half of the negative potential energy. And this will aid us in analyzing particular orbits later on. This is another one of those usable equations under certain circumstances. Another thing that we can look at is escaping orbit. Let's say that you're on Earth and you want to leave Earth and you want to go to the moon, which we've done a few times. And people are starting to talk about doing again. And we're also talking about going to Mars. And we've sent some robots to Mars. But how much energy do you have to give to that guy in order to leave Earth orbit and go someplace else? Now this is a case where we're going very far away. And we call very far away infinity. That doesn't actually have to be infinity, it just has to be very far away. Meaning the force of gravitational attraction from the Earth on our satellite is negligible compared to other things. So if you watch the movie Apollo 13, and you should, it's a very good movie, they talk about in one part of that movie when they have left Earth's orbit and now they're entering the moon's orbit, and the pull on their ship has changed from being towards Earth, from being net towards Earth, to being net towards the moon. So what we'll be looking for here is the escape velocity. How fast do you have to be kicked away from the Earth in order to escape from the Earth's gravitational pull and enter into some other celestial object's gravitational pull? And this being an application of conservation of energy, we have to look at, well, what kind of energies do we have here, and what kind of energies do we have there? Now, we have a satellite, so it has some kinetic energy already, and we're trying to kick it away. And then it also has potential energy because it's a distance away from the center of the planet. When it gets very far away, we're assuming that it has zero kinetic energy because we just want it to barely get very far away. And at that point, it also has potential energy, but we already said that potential energy at very far away is zero. So we're going to see how this works out, how we can start out with both kinetic and potential energy at the beginning and then up with zero of everything at the end. Total energy at the beginning is going to be equal to total energy at the end. We're not allowed to use energy. This is simply an application of the conservation of energy that we've talked about before. And at the beginning, we have kinetic energy. And for satellites, for some reason, I'm not quite sure why, but for some reason we call it U instead of PE. So I'm going to switch from PEs to U's. And at the end, the two kinds of energy that we would still talk about are kinetic energy and potential energy, except here, in order to just barely escape, we're going to end up with zero of each. Kinetic energy is 1/2 mv squared. Potential energy is gmm over r. And then we end up with a big fat zero on the right. Now, once in a while, you'll be asked to find a situation where the kinetic energy is not zero very far away. At which point, this isn't zero, this is something else. Now, let's just rearrange this and solve for v. Notice how it doesn't matter how big the thing is that I'm kicking away from the Earth. What matters is how fast it's moving. It doesn't matter if I'm sending a bullet or sending a whole rocket filled with people. If you've ever watched The Expanse TV show on, I think it's Amazon Prime, they have some discussion of this sort of thing because they're constantly moving between planets and asteroids and moons in our solar system. So they're going from Earth to the moon to Mars to the asteroid belt out to Jupiter's moons. So they have to, every time they leave one planetary object, they have to reach escape velocity for that object that they're leaving, and that depends on how big the thing is that they're leaving. It doesn't matter how big the thing is that they're in. So rearranging this, notice that what matters is what universe we're in. That's your gravitational constant g. What matters is what is the thing that you are leaving and how big is it. So the Earth has one particular escape velocity associated with the Earth, and then the Moon, which has a different mass and radius, has its own escape velocity because of the Moon's mass and radius. And one of the homework problems will be to calculate the escape velocity for various planets and moons in our solar system and come up with a number for each, and then compare how much energy did you have to have at the beginning in order to reach that escape velocity. In the next video, we will look at Kepler's 3 laws and how they tie back to the things that we've discussed today.